In this group of problems, we will consider waves on a string and waves in air columns, vibrations of air columns. And these are important, of course, basic physics of musical instruments. But we begin with an infinite string. So here we have a string. And when there is a wave on it, it is displaced. And let's take a small portion of it. This is at x, this is at x plus dx, this is x. And we are considering a string of mass density mu. And here there is a tension. And here's tension, pulling it this way. And this angle is theta, and this angle is theta, except that everybody is a function of x. So this is theta at x plus dx, this is t at x plus dx. And it is vibrating in a transverse wave, namely orthogonal to x. So every point here is oscillating or moving like this. So the equation of motion for this piece is T, well, net force, if this is the y direction, net force in the y direction is, well, small force delta F, it's delta m times acceleration, and we shall call the displacement y at x at time t. So this is our displacement. This will be mu dx. This is our, and a is acceleration, is second derivative. We take the partial derivative because it's also a function of x, and delta, the thing that is the force in the perpendicular, in the transverse direction that is accelerating this this part of the string is T. All right, so we have this component that is pulling it up, and this component that is pulling it down. So it is T sine theta at x plus dx minus T sine theta at x. So it is dx delta x T sine theta. And sine theta, we are considering small angles. So we will make the approximation sine theta is approximately tangent theta for small angles. And this is dy sine theta is approximately tangent theta, which is equal to dy dx. Therefore, this is roughly tangent theta, and dx, dy dx, 2 of x, delta y, delta x. So this is the force that is accelerating our piece of string here. And when we equate them, dx components cancel. So we have d by d delta x, 2 of x, delta y, delta x. That's equal to mu del square y delta t square. Okay. So this is the equation that the displacement yxt obeys for transverse waves on a string. Notice that although this piece is vibrating or moving up and down, can move up and down, it cannot move sideways to the right or to the left. And to this approximation, when sine theta is like theta, the forces here are equal, and we can take T to be constant. Tension T equals constant. In which case, we can write del square minus 1 over T over mu del square y delta T square is equal to 0. So this is a one-dimensional wave equation, and this we shall call U0 square. That's T over mu. U0 is the speed of the disturbance along the string. So for example, if this is a disturbance, this will move with U0. So that's the disturbance. So let me erase this part. We don't need this anymore. All right, I'm erasing all of this. And also for a shorthand, we shall use, this represents this operator acting on y. I'm erasing the figure also, we don't need that anymore. So for t equals constant and mu equals constant, we will deal with this equation. And let us look for the solutions. Remember, we are considering an infinite string. No boundaries. So one can attempt such a solution. Fx minus u0t. This is an arbitrary differentiable function. So we say yxt equals, here there are two variables, x and t, but this is a particular combination of these variables, x minus u0t. So it's only one variable, x minus u0t. So let's call it eta, for example, and let's see how it solves the equation. For example, we need delta f delta x. For y, I'm putting f in this equation. Okay. So I need the derivatives. This is by chain rule, delta x times delta f delta eta. But f is only a function of eta, no other thing. So this is also df d eta, which I will call f prime. And eta is x minus u0t. So this is simply plus 1. So this is f prime. Clearly is f double prime. Double with respect to eta. Now I need this derivative, so let me just take delta u0t. u0 is a constant, I put it inside the derivative. F is delta eta delta u0t. Again, df d eta. But eta is x minus u0t. So derivative with respect to u0t gives me a minus 1. So it is minus f prime. So the second derivative is equal to plus f double. Therefore, is f double minus f double, that's equal to 0. So an arbitrary function of the form fx minus u0 t solves this wave equation, is a solution of this wave equation. Let us see the meaning of this equation. Now I can erase this. Let's just remember that. Let's see what's this function doing. Let's take, for example, at time t equals 0, x. Let us say that, suppose f is something like this. This is fx. Namely, this is fx minus u0 t at t equals 0. The thing to notice is that f is peaked at the 0 of its argument. So let us look at it at a time t later. Time t later, we have fx minus u0 t. But this will be peaked. This will be peaked at the value when its argument eta, which is x minus u0 t, is 0. So this is u0 t, and here it is peaked. Okay. It's clear that this is moving to the right with speed u0. So fx minus u0 t, let me summarize. This is my wave equation, and fx minus u0 t is an arbitrary, well, smooth function that represents a disturbance that is going to the right with the speed u0. Now, this is one solution, but this is a second order partial differential equation, and we need another solution. Obviously, that's another wave that is moving to the left with u0. So, what can that be? G x minus u0 t, which is g of x plus u0 t. So the general solution then, I can erase these on the infinite string. And yxt can be written as a sum of two disturbances, one going to the right, the other one is going to the left. All right. This is a linear operator, linear equation. Therefore, if y1 is a solution, and then y is equal to y1 plus y2 is also a solution, obviously. So, at the end of this discussion, you will see a video made by Ugur Guney, in which there is a wave going to the right and another wave. Of course, these are mathematical idealizations, wave going to the left, and they superpose, so you can see the wave shape on such a thing. All right. One of the important form of the solutions is a harmonic solution of this equation. And since it is any function of x minus u0 t, I'm considering a harmonic function that is moving to the right. And I will use the techniques introduced in the when we discussed the oscillator problem in this series. If you look at those, we used exponentials, complex numbers, and phasors. So I will use those because they make the computation very easy. So you can just check those videos. But nevertheless, it's very simple. So suppose we write the solution as some a e to the I kx minus omega t. Of course, this is a complex thing. How can it be realized on a real string? The physical solution, y physical, is the real part of this complex y. And a also may be complex. If it is going to be a solution like this, then y must be e to the I k x minus omega over k t. And again, if it's going to be of the form x minus u0 t, omega over k has to be u0, the velocity. Or we can simply put it into the equation and find the relation between omega and k. Del square y is equal to 0. This is minus 1 over u0 square. So this gives me minus k square, then minus omega square over u0 square. Y is equal to 0. Since y is not 0, this has to be 0. Therefore, omega is equal to u0k. The same thing we found here. Okay, so y, strength, a e to the I kx minus omega t with omega is equal to u0k is of the form x minus u0 t. So it is a sinusoidal wave of amplitude a, and this is moving to the right with the speed u0. So you see, it's the same pattern that is repeating itself from minus infinity to plus infinity. Just take any point x, and then let's ask the question, when does the wave come to the same value? What is the shortest distance after x that the wave comes to the same value? That means e to the I k x plus lambda has to be equal to e to the I k x. Therefore, e to the I k lambda is equal to plus 1. Therefore, k lambda is equal to 2 pi. And lambda is equal to 2 pi over k. So lambda is the wavelength. And k is lambda is the wavelength, and k is called the wave number. Let us ask the same thing for time. Suppose at a certain x and time you have a certain value of y. Then you ask, what is the minimum amount of time after time t that the wave has the same value? That means e to the minus I omega t plus t is equal to e to the minus I omega t. Therefore, e to the minus I omega t is equal to plus 1. That means omega t is equal to 2 pi, and t is equal to 2 pi over omega. Notice that lambda is the shortest distance. You can add 5 lambdas. Okay, it will be the same. So t is the shortest time after time t that the wave will repeat itself. That's 2 pi omega. The period is defined to be as the inverse of f. Therefore, omega is 2 pi f. And if we multiply f and lambda, f times lambda, this is f is omega over 2 pi. Lambda is 2 pi over k. So 2 pi is cancelled. Omega over k. But we defined omega over k as u0. So these are the relations in a sinusoidal wave. It makes sense because if you advance lambda times at each frequency times distance lambda in unit time, you have traveled a distance u0. So it's the distance per unit time is u0. So let's just write omega is equal to 2 pi f. Lambda is equal to 2 pi over k. T is equal to 2 pi over omega. And lambda times f is equal to u0. That's what I will say about the sinusoidal wave on an infinite string. Okay. I'm erasing these. Now we shall consider the energy in this problem, because string is getting displaced. Each piece of mass is getting a kinetic energy, and there is also a potential energy, and we should discuss this. So I am considering a piece of string between x and x plus dx, and I'm considering the energy of this string here, piece of string. So it has a bit of a kinetic energy plus delta potential energy. So we shall consider now what they are. Kinetic energy is obvious. It is 1/2 mass total, and the mass is mu times dx. That's the mass of this piece of string, and its velocity square. All right. Now, what about the potential energy? This piece of string is being pulled by tension, which we assume to be constant for small displacements. And, this, for example, like in the spring problem, if you apply a force and stretch it, you give it to a potential energy. So this piece of string is pulled from both sides by tension. So tension is doing work, and that work is the potential energy gained by that piece of string. So delta potential energy is equal to the work done by the tension. So tension times how much did it stretch? Delta S is the length now, and what was the length before? Delta S, delta X. Now let's look at, this was delta y displacement, this is delta x, and this is delta s for small displacements. And clearly delta s is root delta x square plus delta y square. And of course, we expand. This is delta x root 1 plus delta y delta x square. And for small transverse displacements, this is like delta x times 1/2 times 1 plus 1 plus 1/2 delta y delta x square, etc. All right, so we put this delta s into here. So it is t delta x plus 1/2 delta y delta x square minus delta x there's a delta x here. So this cancels that, and to a good approximation, this is 1/2 delta x 1/2 t delta y delta x square. So that's the potential energy. Therefore, now we can write delta E. That's the kinetic energy. Let me write delta x here. 1/2 mu. It's not the second derivative. Delta y delta, it's the velocity square, not the acceleration. Delta y delta t square plus 1/2 t delta y delta x square, which I will write as delta x times rho e. So this is the energy density on the energy per unit length. Rho e is dE dx. Rho e is the energy per unit length. So rho e is energy per unit length. So that when you multiply it by delta x, we get the energy. Okay, I'm erasing. This is mu dx dy dt, the velocity square. I'm erasing. Now, an interesting question is this. This is the energy density, but we have seen that there are waves traveling with u0 to the right or to the left. And therefore, we can define the current of energy as rho e times u0. Let's look at check the units. This is energy per unit length. And this is length over time, the velocity, E over T. So it's energy per unit time. It is the current of the energy. It's like electric current. It's charge per unit time. Okay, it's the current of energy. Okay, so we defined that. Now, let us take a particular y and compute its energy density and compute the current of energy. And of course, a simplest y you can think of is this harmonic oscillation along the string, namely y is equal to a e to the I kx minus omega t with omega is equal to u0k. So suppose we have such a wave, harmonic wave, this is an infinite wave moving like this. What is the energy density and what is the current of energy for this harmonic wave? So we will compute rho e, but as usual, instead of rho e, let us compute its time average, rho e. And this is the period of the oscillation. Remember, t is 2 pi over omega. And we shall use just the technique we discussed when we studied the oscillation of a mass connected to a spring. Namely, let me just remind you, if A is equal to A0 e to the minus I omega t, if A physical is the real part of this, and if B physical is the real part of B0 e to the minus I omega t, then this is a bilinear term. And here, of course, you must put not the complex things, but the real functions. However, when the variations are harmonic and varying in the same harmonic way with same omega, then this is 1/2 real A0 B0 star or 1/2 real A0 star B0. It's a little formula worth remembering. And now we can just use that very simply here. Rho e is equal to, I have, so this part is rho e. So take the derivative. So I have 1/2 mu times 1/2. Then this will give me omega square and plus 1/2 t. You see, I'm using this delta y delta t is equal to minus I omega y, and delta y delta x is I k y. So it is 1/2 t, 1/2 k square. So it is, and this is u0 square k square. So it is 1/4 k square. And there is an a square multiplying these, the strength of the thing. So it is a square over 4. K square is common. Mu times u0 square plus t. But u0 square is t over mu. So it gives me 2t. So it gives me a square. Then 2t, 2 cancels that. So it is 1/2 t k square. So this is the average energy density per unit length. If we have a sinusoidal wave traveling along this string. What about the energy current? This will become important in later problems. So I is rho e u0 with a time average. IE is equal to rho e u0. u0 is constant. So this is a square times 1/2 t k k u0. K times u0 is omega. So it is a square 1/2 omega t times k. So again, if this is the wave that is traveling, of course, the physical wave is the real part of it. That's the energy density, and that's the average energy density, and this is the time averaged energy current along the string. So such a current is moving along the string. Current of energy. Okay. Thank you.